Welcome to Math with Professor V. In this video, I'll be solving and working through Exam 2 that I just gave my Calculus 3 class summer 2024. If you need a little bit more of an in-depth video lecture on any of the topics that are covered in this video and in this entire unit, then head straight to the description box because I have the video lectures linked that are on the Calculus 3 video lectures playlist. But without further ado, let's jump right in. So the first question dealt with limits, and the directions state, find the limit or show why it does not exist. Now, just as a recap, when you're actually finding a limit and proving that it does exist, you need to either do direct substitution, meaning you plug it in and you just get some sort of number. You need to either factor, manipulate, rewrite cleverly, and then you do direct substitution. Another way that you could prove that a limit exists is you go polar and you compute it and you get some sort of constant. Or you could do the squeeze theorem. And that's pretty much the end of all our tools that we have in multivariable calculus. The only other remaining option is doing a delta epsilon proof, but I told them that wasn't going to be something they were tested on. When you show that a limit does not exist, that's when you show that the limit along two different paths has different values. That is never the way to show that a limit does exist. So this is to show that it exists as a finite number. You have four options. When you're testing paths, that's only to show that a limit doesn't exist. Remember, there's infinitely many paths that we can take when we're in 3-space plus. So it's not as basic as when you're in Calc 1, you check the limit from the left is the same as the limit from the right and you can call it a day. No, it's not that straightforward. There's infinitely many paths. So if we're testing paths, it's because we think the limit doesn't exist. Okay, so now let's actually do the problem here. If you try to use direct substitution and just plug in 0, 0, you're going to get 0 over 0, which is an indeterminate form. But I'm looking, the numerator has 4 terms. I'm tempted to try factoring, and then maybe I will be able to use some direct substitution. So I'm going to rewrite limit xy goes to 0, 0. They're letting me know x is different from y. That way I don't have to worry about the denominator being 0. And I'm going to proceed with factoring. So 4 terms I can factor by grouping. So from the first 2 terms, only look at the first 2, I can take out an 8. And then I have rad y minus rad x plus, and then keep in mind this x is rad x times rad x. So I can factor out a rad x from the next 2 terms. And then I'm left with rad y minus rad x. Do you see that? That was maybe a little sneaky, but we like it. And then in the denominator, we still have rad y minus rad x. I'm going to put parentheses around it so we know to keep that together, that factor. Now, you can factor completely or, at this point, they're very advanced. They can cancel at this step, and I'm not going to get mad at any of them. Their algebra skills are on point. So we see rad y minus rad x is a common factor in the numerator. And then we're left with 8 plus rad x as the other factor in the numerator. And then we still have rad y minus rad x downstairs. Fabulous. Then we can cancel out rad y minus rad x. And notice you need to keep writing lim every step of the way until you actually evaluate the limit, until you substitute in the values for the variables. So x and y are going to 0, 0. I'm just left with 8 plus rad x. So substituting in 0 for x, notice I'm not writing lim anymore. And then this is just 8. Good? Beautiful. For the most part, everyone got it just fine. Next one, problem B. Limit as xy approaches 0, 0, xy squared cosine y over x squared plus y to the 4th. Okay, now you can play around with this one a little bit. In this particular case, direct substitution doesn't work. Again, you have 0 over 0, but the limit does not exist for this particular function. So in order to show that it doesn't exist, I need to find two different paths that have different limits. So some students did this a variety of ways. Some went along the x-axis or the y-axis. I thought the most efficient way was to go along a general linear path, y equals mx. But like I said, a variety of approaches would have gotten a full credit response on this problem. So if we're going along a general linear path, we're looking at the limit as x mx approaches 0, 0. And I'm going to substitute in mx everywhere I see y. So I have x mx squared cosine of mx over x squared plus mx to the fourth. Good? Okay, so then this is the limit as x mx approaches 0, 0 of, let's see, we've got x cubed m squared cosine mx in the numerator, and then x squared plus m to the fourth x to the fourth down below. I can cancel out x squared from everybody. So this will just be x to the first. This will become a 1, and then that'll become x squared. So then now we have the limit as x mx approaches 0, 0 of x m squared cosine mx over 1 plus m to the fourth x squared. Okay, so let's see. If I try direct substitution now, am I going to actually get a constant, a value for this limit, or are we in trouble again? So let's try. X is 0 times m squared times cosine of m times 0, so that's just 0, over 1 plus m to the fourth times 0 squared is 0. Oh, this is going to be fine, because in the numerator we have 0, but in the denominator, thankfully, we don't. We have 1, so 0 divided by 1, 0. So this approach is nice. I like doing this going along y equals mx because it generalizes along any linear path that has a slope, right? So not along a vertical line, but still it kind of condenses you testing various paths. Like I said, though, if they tested along the x-axis or the y-axis, the result was the same, they got 0. So how to pick a path that doesn't get you 0, you actually have to go along a non-linear path. And a tip that I told them that's helpful is if you look at sometimes the denominator, you have y to the fourth and x squared. Try to get them to be the same term. That way you can cancel out hopefully something and get a different value. So it's usually easier to let the smaller powered term be the one that you substitute in for to make it match the larger one. What do I mean? I'm going to go along the path x equals y squared. If I let x equal y squared, then I'm going to have 2y to the fourth in the bottom, and that's probably going to do it for me. Okay, so without further ado, let me quit yakking and get into it. So along x equals y squared, we're going to take the limit as xy, actually x is y squared, so let me write y squared y goes to 0, 0 of, and then remember the original function, now I'm going to replace all of the x's with y squared. So then I have y squared times y squared cosine y over y squared squared plus y to the fourth. And then notice, this is gonna be perfect. Y squared y approaches 0, 0. I have y to the fourth cosine y upstairs. 2y to the fourth in the denominator. Those cancel. And then we have the limit now as y squared y approaches 0, 0 of cosine y over 2. And then if I substitute in 0 for y, cosine of 0 is 1. So the limit along this path, x equals y squared, is 1/2. So notice these two limits are not equal. So whenever different paths have different limits, that tells me the limit as xy approaches 0, 0 of the original function xy squared cosine y over x squared plus y to the fourth does not exist. That's the multivariable version of saying, limit from the left doesn't equal the limit from the right. It's just we have infinitely many paths to check. So that's why checking paths is never an appropriate way to show that a limit does exist. There's infinitely many paths to choose, and I hate to break it to you, but you're not going to live long enough to test them all. So that's not the way to go. Okay, moving on. Let's look at problem 2. At what points is the given function continuous? Be sure to use appropriate notation. So all of the functions here that are given in problem 2, we can apply a special theorem to that we learned early in our calculus career, and namely that is that rational functions, radical functions, inverse trig functions, exponential functions, all these functions are continuous on their domain. So all these functions are continuous on their domains. So all we need to do in order to answer the question about where are they continuous is identify the domain for each function. And they just need to use appropriate notation and make sure they're in the right dimension. That was really the crux of the problem. So 2a f of xy is x minus y over 2x squared plus x minus 6. If you look here, this is a rational function. I know the domain of a rational function includes all values for, in this case, x and y, such that the denominator is not 0. So let's go ahead and see what we need to restrict from the domain. I'm going to set 2x squared plus x minus 6 equal to 0. Now this factors. It factors into 2x minus 3 and x plus 2. So I can see my restrictions would be x equaling 3/2 and negative 2. However, I have no issue with any of the y values, right? There were no y's in the denominator, so we don't need to restrict y. So if we're asked where is the function continuous, on all x comma y, you have to indicate that the domain is in 2 space, it's in R2, such that x cannot equal 3/2 or negative 2. That's the answer for 2a. Good? Beautiful. Okay, moving on. G of xy equals rad x plus rad 1 minus x squared minus y squared. So what do I know about radical functions? Well, the radicand, the stuff underneath the radical sign, has to be greater than or equal to 0. So what that means is x has to be greater than or equal to 0. And also we require 1 minus x squared minus y squared to be greater than or equal to 0. Now this inequality is solved. I'll leave it alone. This one, no, that's not how I'm going to list it in my domain. I need to move the variables over to the other side and rewrite this as x squared plus y squared is less than or equal to 1. Isolate the variables as much as possible. Okay, so both of these conditions have to be satisfied in order for g of xy to be continuous. So not only does x have to be greater than or equal to 0, but also x squared plus y squared has to be less than or equal to 1. So we're just going to go ahead and list both those conditions. So g of xy is continuous on all xy such that both inequalities are satisfied. And it's just as simple as listing them side by side like that, with a comma to separate. Okay? Very good. Next one, f of xyz equals arcsine of x squared plus y squared plus z squared. So think back, what sort of values are we allowed to plug in to arcsine or to sine inverse? It's the range of sine. So those values have to be between 1 and negative 1 inclusive. So that means x squared plus y squared plus z squared has to be greater than or equal to negative 1 and less than or equal to positive 1. Now, this lower bound is redundant because x squared plus y squared plus z squared is always automatically greater than or equal to 0. So really, I could just leave it off and only write x squared plus y squared plus z squared is less than or equal to 1. And notice in this case, the domain are ordered triples, x, y, z. So we're in three-dimensional space, so we need to make a note of that. So f is continuous on all x, y, z such that x squared plus y squared plus z squared is less than or equal to 1. Okay, beautiful. Now some of them, I think they were paranoid. They left this on when writing where the function was continuous. It's not wrong to, it's just not necessary. So I didn't take points off. If you're watching and you're in my class, don't worry, okay? Or if you switched it to 0, you didn't need to, but it's fine. Okay, last one, f of x, y, z equals e to the x over e to the y plus z. So this is a rational function, and I just want to make sure the denominator is not 0, but that's impossible. E raised to any power is never 0. So that means I have no restrictions. So we just have to be careful that we list the domain correctly. The domain is going to be all of R3. So they literally could have just written this. Some really wanted to write it out in set builder notation. Okay, fine. So you can write x, y, z such that x can be any real number, y can be any real number, z can be any real number. There's a variety of ways. X cannot be part of R3 though, right? X, y, and z are each one-dimensional quantities. Altogether, this gives me R3. What was not appropriate was someone who wrote, or if someone wrote, all real numbers. Why is that a problem? All real numbers means all of R1, the entire real number line, that's a one-dimensional quantity. But the domain here, or where f is continuous, is 3 dimensions, yes? So this doesn't make any sense. Wrong dimension. If this was stated by itself, x can be any real number, but then you also need to go state y is any real number and z is any real number, okay? Good. That was the only thing that some people messed up on, and I understand, because up until now, you've been able to say all real numbers, and that's been sufficient, but we have to be more precise. Okay, very good. Question 3, define f of 0, 0 in a way that extends f of x, y to be continuous at the origin. So let's go over our definition for continuity. So to be continuous at the origin, what does our definition tell us? 1, f of 0, 0 is defined. Well, we're being asked to define it, so that's still up in the air. 2, the limit as xy approaches 0, 0 of f of xy exists as a finite number. And 3, f of 0, 0 is equal to the limit as xy approaches 0, 0 of f of xy. So, in order to satisfy all 3 conditions, what I need to do is find the limit of this function as we approach the origin. Whatever that limit is, I'm going to say that's how f of 0, 0 should be defined, and then I will satisfy the 3rd condition as well. Okay, so really this problem boils down to, let's take the limit as xy approaches 0, 0 of this function here, 4x squared minus x squared y plus 4y squared over x squared plus y squared. This is a beautiful time to go polar. So by going polar, I mean you're going to substitute in x equals r cosine theta, y equals r sine theta, x squared plus y squared is r squared. And this works when we go towards the origin, because then as x and y go to 0, 0, r also approaches 0, but make sure that you indicate it's always through positive values from the right. This only works if we're going to the origin, because then it's independent of what theta is doing. Theta can spin around its little heart. If r is going to 0, we're going to the origin. Theta is not stopping us. Okay, so let's go polar and try to evaluate this limit. I'm inclined to do that. Let me clarify why. I saw x squared plus y squared here, and then I saw 4x squared and 4y squared, and then it was just saying, Professor V, you should go polar. Now's the time, if there was any. So in the denominator, hopefully you can see that's just going to be r squared. And then in the numerator, 4x squared plus 4y squared is 4r squared. And then minus x squared y, so that's going to be r squared cosine squared theta. That's x squared, and then r sine theta is my y. Good? Okay, well, hopefully you're noticing r squared cancels throughout the limit. Beautiful. And then now I have the limit as r approaches 0 from the right of 4 minus, let me put r cosine squared theta, sine theta following. And that's all that's left. Now, as r approaches 0, 4 isn't changing, that's a constant. Then I know this term right here is approaching 0. And cosine theta times sine theta, or cosine squared theta times sine theta. The only thing that I'm nervous about is if those were to approach infinity, because 0 times infinity is an indeterminate form. But if they're approaching anything other than infinity or negative infinity, we're good. I can evaluate the limit. And I know something very special about cosine and sine. Those are bounded functions. They're bounded between -1 and 1. And so this product is also bounded. There's absolutely no chance that it's going to go to infinity, which is perfect for us. Because then if I have r approaching 0 times something that's bounded, then for sure this entire term right here is going to 0. That's going to 0. So this limit is equal to 4. Perfect. So since the function approaches 4 as we approach the origin, that's how I should define f of 0, 0 in order for the function to be continuous at the origin. So what I'm going to do now is write out the piecewise function. It's equal to 4x squared minus x squared y plus 4y squared over x squared plus y squared if xy is not equal to 0, 0. And then we're going to define it to be 4 if we're at the origin, if xy is 0, 0. Okay, good. This was a nice opportunity for them to show that they knew how to switch to polar when taking limits. Okay, and that they understood the definition of continuity. All right, moving on. Next topic was the chain rule. So write a chain rule formula for the following derivative. We want del w del t for w, which is a function of x and y and z. So I'm going to make a tree diagram. W is a function of 3 variables. And then x is a function of 2 variables, r and s. Y is only a function of 1 variable, t. And z is a function of 3 variables, r, s, and t. And so we have to write the chain rule formula for del w, del t. So what you should do, if you make a nice tree diagram, find all the branches that end with the variable that you're differentiating with respect to, and then start at the top of the tree and trace your way down. So to get to those 2 t's, we have to go down these 2 branches. That's all there is to it. So this first branch, this is del w, del y. I have a partial derivative del because w is a function of more than 1 variable. So that's del w, del y, times, I got to go all the way down the branch. You multiply as you keep going down. Dy dt, not del, dy dt. Y is only a function of 1 variable, so that is not a partial derivative. So a lot of people miss that. Plus, now when you go to the next branch, you add del w, del z, that's a partial, times del z, del t, because z is a function of more than 1 variable. Good? Great. Love it. Okay, next one. Evaluate del z del v at uv equals 1, 4 for the function z equals xy squared minus natural log of x equals e to the u plus v, and y equals u times v. And you must include an appropriate chain rule formula as part of your solution. So again, z is a function of two variables, u and v. And then, oh, hold on, I jumped the gun. Z is a function of, let me look at z, poor z. Z is a function of x and y. X is a function of two variables, u and v. And y is a function of two variables, u and v. Okay, so del z del v, find all the branches that end with v and trace them down. These are all going to be partial derivatives. Del z del x times del x del v plus del z del y times del y del v. Okay, del z del x, we're just going to take the partials as we go. Treating x as constant, del z del x will be y squared minus 1 over x. Del x del v is just going to be e to the u plus v times 1. So e to the u plus v. Plus del z del y would be 2xy times del y del v, holding v as variable, u as constant, would just be u. Beautiful. Now they told me that u is equal to 1, v is equal to 4. That means x would equal e to the 1 plus 4, which is 5. And then y equals 1 times 4, which is 4. So I can substitute all these in now. Y squared, that's 16, minus 1 over x, which is e to the 5th, times e to the u plus v, that's e to the 5th, plus 2xy, so 2 e to the 5th times 4 times u, which is 1. If I distribute here, now I'm going to have 16 e to the 5th minus 1 plus 8 e to the 5th. So final answer, 24 e to the 5th minus 1. Good? Great. Most of them did just fine on this problem. Okay, next one, 5a. Use implicit differentiation to find the specified derivative at the given point. We need to find del y, del x at the point 613 for the following function. So if I call this capital F of x, y, z, we can use that little shortcut formula I showed you guys in the lecture. Del y del x is negative partial with respect to x over partial with respect to y. And I think everybody did it this way. So here we go. Negative. Partial with respect to x, let me highlight it. So derivative of 2x squared would be 4x minus derivative of 3 ln xz would be 3 over xz. And then you have to do the chain rule, multiply by the derivative of xz with respect to x, which is z. And then everything else would just go to 0. Partial with respect to y, the only term that has y in it is 3yz squared. So the derivative would be 3z squared. Good? Okay. Then this z actually cancels out. So we're left with negative 4x minus 3 over x over 3z squared. And then I'm going to evaluate this at 613. So then we have negative 4 times 6, that's 24, minus 3 divided by 6 is a half. Over, why did that become a subscript? That's bizarre. Okay, over 3 times z squared is 9. So 24 minus a half, that's 48 halves minus 1 half, that's 47 halves. Negative 47 over 2 over 27, and then bring the 2 down there, So we have negative 47 over 54. Good? Excellent. Okay, the radius and height of a cylinder are changing with time. At the instant in question, R is 2 centimeters. This is supposed to be plus 3 centimeters. Thank you to my stellar student who caught that and came up and pointed it out. I told them all. That should be a plus, but everything else should be negative. dr dt is negative 3 centimeters per second, and dh dt is negative 6 centimeters per second. At what rate is the cylinder's volume changing at that instant? You must include an appropriate chain rule formula as part of your solution. So volume of a cylinder is given by pi r squared h. So V is a function of r and h. However, r and h are only a function of t. So when they want the rate of change of the cylinder's volume, that is not a partial derivative. They want dv dt, which will not be a partial derivative. To get there, we're going to take partial derivatives. I'm going to have del v del r times dr dt. Notice, these were not partials. I was already giving them a hint. Plus del v del h times dh dt. That needed to be clearly written. The del's need to look different than d's. Okay, from here we can go ahead. Del v del r, so take the derivative of pi r squared h with respect to r. So it would be 2 pi r h times dr dt. Let me just leave everything with the variables. I'll put constants in just a second. Del v del h, if I hold everything constant except h, the derivative would be pi r squared and then dh dt. Good? Then let's go through, substitute in all the info they gave us. So 2 pi, r is 2, h is 3, dr dt is negative 3, plus pi times r squared is 4, and then dh dt is negative 6. So what do we got here? 4 times negative 9, negative 36 pi, minus 24 pi. This tells me dv dt, not del, is negative 60 pi. The units would be centimeters cubed per second. If you ever need help figuring out the units, I don't like to keep them in the problem. It's not chemistry or physics class. It just kind of makes things messy. So just check V over T. That's what the units should be for over here. V, volume, is measured in centimeters cubed in this problem. T is being measured in seconds. And there you go. Okay. All right, halfway through the test. Moving on. Suppose that over a certain region of space, the electrical potential V is given by the following function. So 6a says, find the rate of change of the potential at the point P in the direction of the vector V, which is I hat plus J hat minus K. So what they're asking for, they want the rate of change of the potential. The potential is V. They want the directional derivative of V in the direction of this vector that's given here. So when we find a directional derivative, we need to first send it in the direction of a unit vector. So V here that was given, 1, 1, negative 1, I'm going to make a unit vector. Its magnitude is rad 3, yes? So 1 over rad 3 times 1, 1, negative 1. So what the problem wants is the directional derivative of V, okay, in the direction of U. So how do we compute that? Well, we know that's equal to gradient of V dotted with U. And then we'll evaluate it at the point P. So gradient of V, let's come along, find the gradient. Partial with respect to x would be 10x minus 3y plus yz. Partial with respect to y, negative 3x plus xz. And then partial with respect to z is xy. Now let me find the gradient at the point P, 3, 4, 5. It's going to be 30 minus 12 plus 20, negative 9 plus 15, and 12. So we get 38, 6, and 12. Okay, so we're almost done. Directional derivative at 3, 4, 5 is 38, 6, 12, dotted with 1 over rad 3, 1, 1, negative 1. Now the 1 over rad 3, you don't need to distribute. You can just keep it out and then add it on, dot the vectors. That's one of our properties of dot product, which is beautiful. So I can just write 1 over rad 3. This is going to be 38 plus 6 minus 12, which gives me, oh my goodness, I ran out of room. What a rookie. Okay. Which ends up being 32 over rad 3. Okay. No, you don't need to rationalize. Some did, though. That's fine. Okay. In which direction does v change most rapidly at p? As we know, that's in the direction of the gradient. This problem asks for what direction, so our answer should be a vector quantity. So in the direction of the gradient of v, which has components 38, 6, 12. If they wanted to scale it down, it would still be in the same direction. So another appropriate answer would be 19, 3, 6. That's it. Lastly, what is the maximum rate of change at p? The max rate of change is equal to the magnitude of the gradient at p. You have to use the actual components of the gradient at p, not scaled down, because the maximum rate of change is going to be a scalar quantity. If you use this scaled down version, that's going to affect the value, the magnitude of this scalar quantity, which will not accurately capture the rate of change. So when you're talking about directions, reduce, do what you want. But when you actually want rates of change, scalars, just like when you want distances, you can't just go reducing or changing the components of your vectors, okay? Dangerous, dangerous. Rad, 38 squared plus 6 squared plus 12 squared, which is rad 1624. And don't worry, they had their calculator. Just reduce this to 2 rad 406. You do need to reduce your radicals, simplify them completely. I don't require you to rationalize. That's simplified. That's simplified, but you can't leave it like this. Okay, that's that. Moving on. Next question. Write parametric equations for the tangent line to the curve of intersection of the surfaces z equals 10x squared plus 3y squared and z equals x plus y plus 11 at the point 113. Okay, we know this is a paraboloid and this is a plane. And they're intersecting. So I'm going to draw a very rough sketch just to kind of show what's going on. Here's my paraboloid. Do you love it? Have you ever seen such a beautiful paraboloid? And then here's the plane coming, intersecting, and they have a curve of intersection. You could probably imagine, right? It's going to cut through somewhere like that. And they want the equation of the tangent line to this curve of intersection at some point here on that curve of intersection. Well, what do we know about the gradient vector? I know that if I call this f of xyz, let's go ahead and do that. So I'll say f of xyz equals 10x squared plus 3y squared. The gradient of f is orthogonal to the tangent to any curve on this surface. Therefore, the gradient is going to be orthogonal to this curve of intersection. Similarly, if I call the plane's equation g of xyz That's x plus y plus 11 minus z. Again, the gradient of g is going to be orthogonal to any tangent, to the tangent, hold on, let me write it properly, to the tangent to any curve. Now, since I'm interested in the tangent on the curve of intersection, this tangent's direction vector is going to be orthogonal to the gradient of g as well as the gradient of f. So the direction vector of our tangent line on the curve of intersection is orthogonal to both the gradient of f and the gradient of g. So how could I get our direction vector? By taking the cross product of the gradients at that point 1, 1, 13. Okay, so here we go. It's pretty straightforward, but the reasoning, I want it to click. So the gradient of f would be, oh, I forgot to do minus z. I'm adding it in now. Okay, hopefully I didn't screw you up. 20x, 6y minus 1. And then gradient of g would be 1, 1, negative 1. I need to first, I mean, you could cross them now, but why? I would evaluate them at the point 1, 1, 13. Since g is a plane, that doesn't change. The gradient won't change. But now I have 26, negative 1, 1, 1, negative 1. So direction vector of my line comes from taking the cross product of these two vectors. And it'll be what? Negative 6 plus 1, negative 1 plus 20, 20 minus 6, which gives us negative 5, 19, 14. Good, so those are the components for the direction vector. Now I can write the parametric equations. X equals negative 5t plus x naught, 1. Y equals 19t plus y naught, which is 1. And then z equals 14t plus z naught, which is 13. Good? Pretty much everyone got it right. It's just understanding how to start the problem that's the trickiest, but the actual computation's not bad. Okay, moving on, linearization. So find the linearization of the function at the given point. So remember, if we're finding linearization L of x, y, z, that equals f of ABC plus partial with respect to x evaluated at your point P times x minus x naught plus partial with respect to y at P times y minus y naught plus partial with respect to z at P times z minus z naught. And x naught, y naught, z naught are right here. So let's go ahead, let's get all our partials and then put everything together. This was hopefully a straightforward one. So partial with respect to x, derivative of ln something is 1 over the something. And then you're going to have to apply the chain rule, multiply by the derivative of what's inside with respect to x. So that would just be 7. And then similarly, partial with respect to y is 9 over 7x plus 9y minus 7z. And partial with respect to z is negative 7 over 7x plus 9y minus 7z. And then now let's evaluate them all at the point P. So fxp is going to be 7 over 7 times 1/7 is 1, 9 times 1/9 is 1, and negative 7 times negative 1/7 is 1. So this is 7/3. Similarly, fyp, I always think of TikTok now. fyp, okay, 9/3, which is 3. And then f sub zp is negative 7/3. And then the only other thing I need is f of ABC. You know, I should have called it x naught, y naught, z naught. Whatever. Every book calls it something different. So f of 1/7, 1/9, negative 1/7 would be ln 1 plus 1 plus 1. So ln of 3. Okay, good. Let's put it all together. So L of x, y, z equals ln of 3, here so you could see the formula, plus 7/3 times x minus 1/7 plus 3 times y minus 1/9 minus 7/3 times z plus 1/7. Yes? Yes, Professor V. Okay, so then what's this going to be? Let's clean her up. ln of 3 plus 7/3 x minus 1/3 plus 3y minus 1/3 minus 7/3 z minus 1/3 again. Oh my goodness. So at long last, we can just say this is, you could put, I don't know, let's put the variables first. It'll look cuter. 7/3 x plus 3y minus 7/3 z, negative 1/3, negative 1/3, negative 1/3 is negative 1 plus ln of 3. Beautiful. So they could put it in whatever order they want on the right hand side. Oops, I don't care about that. This needed to be simplified. This needed to be simplified, and they have to write L of x, y, z. That it's the linearization. It's not actual f of x, y, z. No, no, no. Okay, we're in the home stretch. They have 2.5 hours to take their test. Don't worry. Find all the local maxima, minima, and saddle points of the function. Format your answer in the form of an organized table showing all work. Okay, so in order to get critical points, we have to find where both the partial with respect to x and y are simultaneously equal to 0. So it's partial derivative time. So partial with respect to x is 4x cubed minus 4x. We set this equal to 0. So factoring out 4x, I'm left with x squared minus 1. So that tells me either x is 0 or x is plus or minus 1. Yeah, you'll notice I didn't put any questions where all I asked was for them to find partial derivatives because they just needed to do it throughout the test. Okay, partial with respect to y would be 3y squared minus 3. I'm also setting that equal to 0. So then you get y squared is 1. So y is plus or minus 1. So each of those y values gets paired with each of the 3x values. So I'm going to have a total of 6 critical points. And then I'm going to apply the d-test to see whether these critical points are relative mins, maxes, or saddle points. And I need my second partials in order to do that. So fxx, second partial with respect to x is 12x squared minus 4. Fyy, second partial with respect to y is 6y, and then mixed partial fxy is 0. Okay, so here we go. Let's list the critical points. Second partial with respect to x, second partial with respect to y, mixed partial, the sign of d, classification if it's a relative min, max, or saddle point, and then actually give the function value. This is exactly how I did it in the lecture and how we practiced in class. So they knew what to do. So let me list all the critical points. 0, 1, 0, negative 1, 1, 1, 1, negative 1. I mean, they could do that in any order, but whatever. Negative 1, 1, and then negative 1, negative 1. Okay, beautiful. Yay. Actually, this one, I just want to scoot it, right? Don't we? Yeah. So what helps, I think, is if you list right up above what those partials were. So this was 12x squared minus 4. This was 6y, and this was just 0. So that's easy. 1, 2, 3, 4, 5, 6. Okay, so f(x)(x), this is going to be -4, -4. I'm substituting in the x coordinate only. It's only dependent on x. Second partial with respect to y is going to be 6, -6, 6, -6, 6, -6. Now d, if you'll remember, d is f(x)(x), fyy minus fxy squared. So what's so nice when you make the table this way is it's easy in your head. You multiply these two and you subtract the square of this column. Well, this whole column is 0. So literally you're just multiplying these two. Tell me if it's positive or negative here. So negative, positive, positive, negative, positive, negative. Everywhere where d is negative, we have a saddle point. That's a saddle. That's a saddle. That's a saddle. Now, where d is positive, I have to go back and check what the sign is on second partial with respect to x. So if second partial with respect to x is negative, then it's a local max. And then if it's positive, then it's a local min. And this would also be a local min. If you forgot all that, then just go back to the video lecture where I explained it. Okay, and then the function values, f was x to the 4th minus 2x squared plus y cubed minus 3y. So the z values, or f of xy, should be -2, 2, -3, 1, -3, 1. And just having this table is the answer that they needed. They didn't need to explain any more or format it differently. Good to go. Okay, last question. Use the method of Lagrange multipliers to find the extreme values of the function subject to the given constraint. So we want all extreme values, absolute mins, and absolute maxes. Okay, so here's my function. This is the constraint equation. So g of xy is x squared plus 2y squared minus 2. I mean, the 2 is irrelevant. And so using the method of Lagrange multipliers, I'm going to solve that the gradient of f is equal to lambda times the gradient of g. Gradient of f, let's see, 2x 12y squared equals lambda times gradient of g is 2x and 4y. So now we're going to set up a system of equations equating the corresponding components. So first components equaling each other means 2x equals 2x lambda. 12y squared equals 4y lambda. And then our third equation is always the constraint equation. X squared plus 2y squared is 2. So we have to solve this system. I'm going to begin with equation 1. And no, you cannot divide by x on both sides. We want all extreme values, and x equaling 0 is a very real possibility. So don't chuck it out the window. 2x minus 2x lambda is 0. This is legal. You can do this. And now factor out a 2x, and I have 1 minus lambda is 0. So this results in either x equaling 0 or lambda is 1. Perfect. If x is 0, we're going to go straight to equation 3, and then I can solve for y. Why will that not straighten up? Has it just had it? So if x is 0, into 3, we have 0 squared plus 2y squared is 2, which means y squared is 1, y is plus or minus 1. Now those y values came from substituting in 0 for x. So those all go together, 0, comma, plus or minus 1. If lambda equals 1, the only other place I can go now is equation 2. And you guys, I do recommend that you write down what you're thinking, what your process is, for multiple reasons. One, so when you look back at your work, you can follow your own train of thought. Maybe you were really in the zone and then later on you're not. So it's hard to be like, where did that step come from? Another reason is when someone's grading your work, if you mess up, but at least they can see what you were trying to do, then you can hopefully get more partial credit because I'll be like, oh, they meant to do this. So the more you can communicate, the better. Lambda equals 1 goes in equation 2. Yes, it does. So we have 12y squared equals 4y. Again, no naughtiness, please. Don't cancel out y on both sides. 12y squared minus 4y is 0. Factor out of 4y, and you have 3y minus 1 is 0. So either y is 0 or y is 1/3. What do I do with those two pieces of information? Now we can go into equation 3. So if y is 0, I have x squared equals 2, so x is plus or minus rad 2. So that comes from y equaling 0. If y is 1/3, then I have x squared plus 2/9 is 2. 2 minus 2/9, that's 18/9 minus 2/9. So x is 16/9. X can be plus or minus 4/3. That came from y equaling 1/3. So x is plus or minus 4/3 if y is 1/3. So I have to substitute 1, 2, 3, 4, 5, 6 different points into my function to determine what my absolute max and min are. So let me remind you, f of xy was x squared plus 4y cubed. Okay, here we go. So y is raised to an odd power. I'm going to have to plug in 0, 1, and 0, -1 separately. But the others, since x is raised to an even power, it won't make a difference if it's plus or minus. Do you see what I'm saying? Oh, good. Okay. These have to be separate. So f of 0, 1, that's 4. 0, -1, -4. Rad 2, 0, or negative rad 2, 0 is 2. And I did this already. It's 52/27. So there you have it, folks. There's our absolute max. And there's our absolute min. Let's box them once again. Beautiful. Okay, I hope you had a good time following along. However, the fun does not end there. No. I really like to do just a little bit of wiggle room. I put a couple extra credits. The deal with the extra credit is there's no partial credit, but I like to give people a buffer when they take a test, okay? Find the point on the curve of intersection of the paraboloid and the plane that is closest to the origin. Closest to the origin means we're trying to minimize distance from some arbitrary point to 0, 0, 0. So we know our distance formula from xyz to 0, 0, 0 would be rad x minus 0 squared plus y minus 0 squared plus z minus 0 squared, right? And it's a pain minimizing a function with a radical in it, because whether or not you try Lagrange multipliers or you're going to go ahead and use the methods of the previous lesson, you're going to take some partial derivatives. They're not going to be cute. So what we typically do is instead we minimize the square of the distance so we don't have to contend with the radical. Now, you could do this a couple different ways. I'm going to use the method of Lagrange multipliers, and you can choose to have two constraints. Namely, you're minimizing the distance subject to the fact that this ordered triple xyz needs to be on both the parabola and the plane. So then you would have lambda times the gradient of one constraint plus mu times the gradient of the other constraint. However, what's a little bit nicer is I'm looking and they both have 2z in them. So I'm actually going to find the curve of intersection first and then only consider one constraint. Namely that the point is on the curve of intersection, and I'll reduce the number of variables, therefore simplifying the problem. So the curve of intersection, notice the paraboloid, I can solve for 2z, and I can also solve for 2z in the plane. So let's just work with the plane first. 2z equals y minus x. Let's put that into the paraboloid's equation. Now I have x squared plus y squared. Instead of 2z, I have y minus x equals 4. And not only have I reduced the number of constraints, I've also reduced the number of variables that I have to deal with, because the curve of intersection now only involves x and y. So I can say my constraint is just g of xy, which is x squared plus y squared plus y minus x minus 4. Now, if it still had z's in it, that would be fine. My gradient's just going to have fewer components. And I don't even need to consider z minus 0 now in my distance formula. I'm just going to work with x and y since this is independent of z. But if z was there, it wouldn't be a problem. You would just have it, you would leave this, but now all I have to do is minimize d squared, which is simply a function of x and y, which is x squared plus y squared. I don't need to put plus z squared. There's no z's here. X minus 0 squared is just x squared. Y minus 0 squared, y squared, and we're minimizing the square of the distance. Okay, good. So here we go. This is f. I want to take the gradient of f and set it equal to lambda times the gradient of g. So gradient of f would have components 2x, 2y, times lambda times 2x minus 1, and then 2y plus 1. So let's set up our system of equations. 2x equals lambda times 2x minus 1. 2y equals lambda times 2y plus 1. And then constraint equations, the last one, x squared plus y minus x equals 4. What I started off doing was isolating lambda in equations 1 and 2. So from equation 1, I have 2x over 2x minus 1 equals lambda. And from equation 2, we have 2y over 2y plus 1 equals lambda. And since both those quantities are equal to lambda, I can set them equal to each other. So I can say 2x over 2x minus 1 equals 2y over 2y plus 1. Are you tempted to do anything? I'm so tempted to cross multiply. I hope you are too. Ba-doom, ba-doom. Then we'll have 4xy plus 2x equals 4xy minus 2y. And 4xy just cancels out like a dream. I have 2x equals negative 2y. So x equals negative y. And then from there, I can go into equation 3. If x is negative y, that's negative y squared plus y minus negative y minus 4 is 0. I have 2y squared plus 2y minus 4 is 0. Divide by 2, please. Y squared plus y minus 2 is 0. And this factors into y plus 2, y minus 1. So y is either equal to negative 2 or positive 1. If y is negative 2, then x is positive 2. Or if y is 1, x is negative 1. Because remember, x is negative y. And then we just need to figure out what z value works for each of those. So we know we're going to have 2, negative 2 something, and then negative 1, 1 something. I'm going to go back to the equation of the plane, if you'll remember. You could either plug it into the paraboloid or the plane's equation to get z. So let's see. 2 minus negative 2, that's 4. 2z equals negative 4, so z would be negative 2. And then the other point, negative 1 minus 1, that's negative 2. Move it over, z would be negative 1. So they want the point on the curve of intersection that's the closest to the origin. Well, the one that's closest is negative 1, 1, negative 1. That's our answer. Hopefully you can clearly see it's closest to 0, 0, 0. Why did we get 2, negative 2, negative 2? That's the point on the curve of intersection that's the furthest from the origin. Remember, our method of Lagrange multipliers gives us all absolute extrema. So it gave us the absolute max and min subject to the given constraint. So I'm not boxing this. It's not part of my answer. This one's furthest from the origin on the curve of intersection. Pretty cool. We got bonus info, but make sure you specify only -1, 1. It should be +1. Why did I write a negative? I'm so sorry. Have you been screaming at me for the last 5 minutes? I bet. My apologies. Okay. Last extra credit. Did you see it peeking through? Yes, you did. Okay. One side of a triangle is increasing at a rate of 3 centimeters per second, and a second side is decreasing at a rate of 2 centimeters per second. If the area of the triangle remains constant, at what rate does the angle between the sides change when the first side is 20 centimeters long, the second side is 30 centimeters, and the angle is pi/6? Leave your answer in exact form, completely simplified with appropriate units, and you must also include an appropriate chain rule formula for the problem. So you did need to know area of a triangle is given by 1/2 AB sine theta, where theta is the angle between the sides A and B. So this would be side A, side B, this is theta. Without that, you're in trouble. So A is a function of 3 variables, A, B, and theta, and each of these are changing with respect to time. So let's write the chain rule formula. dA dt would be del capital A del lowercase a times dA dt plus del A del B dB dt plus del A del theta d theta dt. And they're telling me the area of the triangle remains constant. So that means d capital A dt is actually 0. At what rate does the angle between the sides change? So they want d theta dt. And then they've given me one side is increasing at that rate, so I'll say that's dA dt. And a second side is decreasing at that rate, so dB dt, make sure you say that it's -2 centimeters per second. Okay? So let's come through and take all these partial derivatives. So del capital A del lowercase a would be 1/2 b sine theta, and then I'll just leave this dA dt, plus similarly partial of area with respect to b would be 1/2 a sine theta times dB dt, plus, now it's interesting, del A del theta would be 1/2 AB cosine theta times d theta dt. And this actually all equals 0 because they told me the area is constant. It's not changing. Good? Okay, so from here, let's see, the 1/2 cancels out, does it not? Because everything's equal to 0 anyway, so these are all, we can get rid of them. And let me just start substituting in everything that we have. So 0 equals b, I'm calling b the second side. So b is 30 and a is 20. Let me write that down. A is 20 centimeters, b is 30 centimeters. So we'll have 1/2 equals 30 times sine of pi/6, that's 1/2. And then dA dt was 3, plus a is the first side, 20. Sine of pi/6 again, 1/2. dB dt was -2, plus a times b, so that's 20 times 30 times cosine theta, rad 3/2 d theta dt. Okay, so what is this? 90 divided by 245 minus 10 times 2, 20. plus 600 times rad 3 over 2 is going to be 300 rad 3 d theta dt. Okay, so 45 minus 20, that's going to be 25. I'm moving it over though, negative 25 equals 300 rad 3 d theta dt. And then d theta dt, I'll just divide by 300 over rad 3, or by 300 rad 3. So we have negative 25 over 300 rad 3. That reduces, yes. This is going to be negative 1 over 12 rad 3. And then we need units. Theta is being measured in radians always when we're in calculus, and t is in seconds. So this is radians per second. I always want exact answer unless specified otherwise. So they needed this. If they wanted to put a decimal in, the problem didn't ask for it, but it's about 0.048 negative radians per second. You could say the angle is decreasing at 1 over 12 rad 3 rads per second, but you would have to write the word decreasing if you leave off the minus sign. Okay, that's it. I hope you guys enjoyed the video. I hope you enjoyed exam 2 solutions. I didn't finish grading just yet, but I thought at least this way they could get an idea of how they did. I've graded the first 7 questions. I did that in a day, almost a whole day, but I think I should finish this weekend, hopefully, before I see my little angelic class on Monday. So that's it. Like I said, if you need to review any of the topics, check out the video lectures. Also, please follow me on Instagram, TikTok, Twitter. I do all sorts of fun stuff there. I gave a live piano concert last night. Yes, I did. So go to my other socials. Thank you guys so much for your support. I love you all. I'll be back sooner than later. Bye.